Hello, this is a little talk about the calculations, ideas, principles behind the Chem 102 lab analysis of vinegar. So let's get going. First off, vinegar is an aqueous solution of acetic acid, so it's acetic acid in water. Acetic acid, unlike the acids you maybe talked about so far, those are usually called mineral acids like hydrochloric acid or sulfuric acid or phosphoric acid. But acetic acid is something called an organic acid because it involves carbon-carbon structures. And we can see here, over on the right-hand side of the slide, we see a structure of acetic acid. And it has 4 hydrogens, but only one of those hydrogens is actually an acidic hydrogen, can be donated as an H plus by the molecule. It turns out if one of the hydrogens from the carbon was donated as H plus, that would create a very unstable structure, so it just doesn't happen. Donating H plus from the hydrogen attached to the oxygen there, that turns out that is not so unstable, so that does occur. So we're going to analyze acetic acid and vinegar by reacting it with sodium hydroxide. And if we can figure out if we can know, and we'll see how this happens, if we can know when there are equal amounts of acetic acid and sodium hydroxide, and we know how much sodium hydroxide we added, then we can figure out how much acetic acid is there. And that's all possible. So we're going to use a known concentration sodium hydroxide solution. We're going to measure out the volume of the sodium hydroxide we add. We're also going to measure the volume of the vinegar. And the last thing that we don't know and that we'll find is the concentration of acetic acid in the vinegar. So as I was just mentioning, in order to do this, we need to know the special spot where there are equal amounts of the acid and the base combined. And this is often done in a titration experiment. And the figure here is not something that we'll measure. It's actually a little bit more involved measurements of how a titration occurs. And they've measured the pH as sodium hydroxide is added to a vinegar solution. And you can see the pH, every little dot is a different volume of NaOH added, and then the pH is measured at that spot. And you can see that the pH kind of gradually changes at first up to about 20 milliliters, and then it changes very quickly, and then it flattens out again. The important spot we want, the spot where there are equal moles of acetic acid and sodium hydroxide, is that little red dot, and that's called the equivalence point, and it's when you have these equal amounts of acetic acid and sodium hydroxide. And if we use a pH meter and draw this curve, then we can sort of identify it just by sight. It's the little spot where the S, sort of the middle of an S, is this is called an S-shaped curve or a sigmoidal shaped curve sometimes. But the other thing we can do is we can use an indicator that changes color right around where that little dot is. It might change a little bit before the dot or a little bit after. We're going to use an indicator phenolphthalein that changes a little bit after the equivalence point. And so we have to be careful. We want to stop as soon as we see a color. So in the titrations you see me do on, it should look like I'm stopping when I just start to see a constant pink color. That's the color that the phenolphthalein, it goes from clear to pink when it gets pH up around 10 or 11. So just a little bit past the equivalence point. So the procedure we're going to go through is we're going to first, I didn't mention this before, but the sodium hydroxide solution, we need to know its concentration very well in order to calculate the amount of acetic acid. The trouble is it's hard to make up a very precisely known concentration of sodium hydroxide. When we buy it from a company, it tends to have some sodium carbonate impurities, and that acts differently, and so we don't want to we want to sort of be wary of that. Also, it's a very hygroscopic compound. It can pick up water out of the atmosphere, and so sometimes, if it's especially it's been sitting with the top off the container, it'll pull water out of the air, and then when you go to measure it, you're actually measuring out water as part of the mass. It's not just sodium hydroxide you're measuring. This impurity has stuck onto the sodium hydroxide, and so we need to do something called a standardization. That's where we standardize or calculate the exact calculation of the sodium hydroxide. And to do that, we got to use an acid that we do know the concentration of. And to do that, we do have a solution of hydrochloric acid that we know very well. So first off, we're going to measure out a fixed amount of HCl, of hydrochloric acid, add the indicator, titrate it until we see a color change, and right when we see the color change, the moles of sodium hydroxide and the moles of HCl will be equal to each other. And then then from that data we can figure out the concentration of NaOH. Next thing, part B, we use the known concentration of NaOH to figure out the concentration of acetic acid in the vinegar. And again, we'll look for the color change. At that point, the moles of the vinegar and the moles of sodium hydroxide are equal, and we can figure it out. So, as I kind of have mentioned a little bit, but let me just make clear, the moles of H3O plus, or of hydronium, and the moles of OH minus are equal at the color change. And the one little, one of the twists that you're going to see today is that we're actually going to do calculation in millimoles instead of moles. And the nice thing here is that millimoles are just a little bit, they're smaller, and therefore it's kind of like the difference between talk about millimeters and meters. So if I make a measurement and it's 5 millimeters, I can write down 5.0 millimeters, and there I got it. Or I could write down 0.0050 meters, and that would be the same distance, but I have to keep writing down all those zeros before the 5. It's a little bit easier if we just work in millimeters, and similarly, sometimes it's easier to work in millimoles. And I'll talk a little bit about how we do that on the next slide. But so in the NaOH standardization, it's a mono basic compound. It can only react with one H plus, and so the millimoles of OH minus are equal to the millimoles of NaOH. And hydrochloric acid is monoprotic. That just means it can supply one H plus. So at that color change, we can see the millimoles of HCl and the millimoles of NaOH are going to be equal. And similar thing, the acetic acid is monoprotic, and again, we're using sodium hydroxide. So we can say the millimoles of acid are equal to millimoles of base at the color change, and it's just at the color change. So that's why we really got to determine when that happens. So how do we find millimoles? The big thing here is this surprised me when I first heard it, but it really does work out. So usually when you think about molarity, you say, oh, molarity is moles of a solute over volume in liters of the solution. And so yeah, moles over liters. That's sort of everybody kind of picks that up pretty quick in chemistry. But molarity can also be defined as the millimoles of solute over the volume of solution in milliliters. So what's happened here is we've made the number in the numerator, the moles, we made it 1,000 times smaller, but we also made the number in the volume 1,000 times smaller, or I should say 1,000 times bigger. It's a 1,000 times smaller unit, but the actual measurements will be 1,000 times bigger. In any case, those two factors of 1,000, they cancel each other out. And so the ratio of millimoles to volume in milliliters is the same as the ratio of moles to volume in liters. So they're the same value, but if you take the molarity and multiply by the volume in liters, your answer will be in moles. While if you take the molarity and multiply it by a volume in milliliters, the answer will be millimoles. So we're going to do a lot of these calculations in millimoles because the volumes are in milliliters, and so when we take the molarity times the volume in milliliters, our answer is millimoles. And also, as I mentioned before, you don't have to deal with a whole bunch of zeros that you would otherwise, or I should say that you would if you're using moles. So first off, we're going to standardize the sodium hydroxide solution. We start with knowing the amount of HCl, and one key thing is this is going to be the same number of millimoles for all three trials because we use the same molarity HCl that's given in the description of the experiment, and we're going to use the same volume of HCl. So for all three of these trials for the standardization of NaOH, we're going to have the exact same millimoles of HCl. And therefore, we're also going to have the exact same millimoles of NaOH. But each of the measurements has a different volume because we use a burette to deliver the NaOH, and it's a little bit different for the three trials. So you'll get three different molarities of NaOH because the volume of NaOH will be a little bit different for each trial. And then take the average and then use that average in the next step. So the second part of the analysis is vinegar analysis, and what we're going to do here is now we know the molarity of NaOH, that's the average from the first part, and we are going to deliver a certain volume of NaOH that's going to be based off the burette reading. So this millimoles of NaOH will be different for all three trials because we'll have slightly different volumes of NaOH. Therefore, at the end, we can say the millimoles of NaOH are equal to the millimoles of acetic acid at the end point, and we can solve for the molarity of acetic acid. One thing to pay attention to here is the volume of acetic acid. Here, that will be the same for all three trials. You use the same volume for all of the trials. So these acid-base titrations are nice and simple. We don't need to have any equipment. We don't need a pH meter. We can just use an indicator. We can use some glassware. We don't need power. We can just do it pretty easily. And the big thing is that this equality of, or sort of a known relationship between the moles of acid and the moles of base, that occurs at certain spots in the titration, and we call them equivalence point, and we're able to observe the equivalence point based on a color change for this experiment. Sometimes it can be you can do it with a pH meter or with other methods, but we're going to use a color change today. All right, hope you have good luck with this experiment, and if you have questions, let your lab instructor know.